Welcome back to the next session where we're dealing essentially with the atom, the inside bits and the electrons, right? Now, what we're going to be looking at, the bulk of the work in the chemistry we're going to be talking about, involves this rather schizophrenic animal called an electron, okay? The electron is what we're going to be looking at predominantly, how it works, how it moves, and how it interacts, okay, at various levels with other elements, okay, or other electrons belonging to other elements. Now, just once again, to go back to our, we've got an element and we've got an element, right? Remember, sodium and chlorine, okay? Sodium and chlorine. Remember we said they formed sodium chloride, which was salt. The irony, highly toxic metal, highly toxic gas come together and form what we love to put on our food. And in essence, an integral part of life as we know it is salt. Okay? Now, how does this happen? Well, we spoke about ions and positive charges. Remember at the top of the periodic table, +1 hydrogen, +2 beryllium. I'm just going now across in the groups. +3 boron, +-4 carbon, -3 nitrogen, -2 oxygen, -1 fluorine, 0 on the noble gases or the inert gases with helium at the top. They are 0 because they don't interact with other particles or other elements as far as we are concerned at this phase. Now, in order to understand how this happens, we have to go inside. And we have to have a look at what is inside here, okay? How these electrons work when they're spinning around. Let us take what we've got. We've got each element, if you look at each atomic number, increases by 1. Hydrogen is 1. Helium is number 2. Lithium is number 3, okay? Beryllium is number 4. Boron is number 5. Carbon is 6. Okay? Nitrogen 7. Oxygen 8. Fluorine 9. And neon is number 10. We said that each one of these is going up by 1. Now, because we're talking about the electron, I'm going to say that each one's getting an extra electron put in. Remember, elements are not charged, which means that each one, every time an electron comes on, we've got to add a proton into it. Let's leave neutrons out. Those are part of isotopes, remember? And radioactive decay, which we're not going to do. So each time we're going to be adding 1 into this process, right? So what happens? Hydrogen has got 1 electron. So we say, okay, over here, he's got 1 electron. Remember we said that helium has got an electron and another electron, right? Now, we said that if the nucleus is inside there, this is the area called the orbital, right? So around the nucleus, we have got over here, which is called the orbital. Okay, this is the place where the electron sits. Okay, remember, it's the same as the sun with the planets around it, or the earth with the moon. Let's now move it to the sun with the planets, right? Let's say the sun is the core and the planets are our electrons, right? Now you know that mermaids very easily marry just sitting underneath pearls. That's the mnemonic for how the planets work. The first ones. Now, what happens is, if this is now the core, out here we've got the 2 electrons, right? This is hydrogen and helium. But now how do we add another electron in, and another electron in, and another one? Because each time we're adding in, remember, we are increasing the atomic mass. Because we're adding a proton and an electron. 2 extra particles, it's increasing the weight. Okay? Now in these orbitals, we've got to decide, well, how do we fit all of this in? Now, you will see in your books, they talk about a rule, okay? The Pauli's exclusion principle and the Aufbau principle, electrons are lowest available energy levels, and Hund's rule, every orbital is singly occupied before any orbital is doubly occupied, right? So what we do is we do this, okay? Let us take, for example, a nitrogen, right? Let's take nitrogen. Nitrogen. Its symbol is N, and it is number, let's just go back and have a look. It was number 7, okay? Right, so it is number 7. What does that mean? It means we've got 7 protons, 7 electrons. How do we fit these 7 electrons in? Well, they go into orbitals, okay? In the first orbital, okay, we've got space, okay, over there. Remember what we said, we've got space for 2 electrons can fit in there. All right. Why? Because we said I can only put 2 in here. Because if I put more in there, they are too close to each other. They don't want to be there. What actually happens is the electron, the next one that comes in, goes into a different orbital, right? It goes into level 2. So this is first level. This here is second level, right? So instead of being in Mercury, okay, it goes into the Venus orbital, right? Mercury's full. There's only space for 2 electrons in there, all right? And according to the rules, the electrons must go in paired like that, right? That is the 3 rules that we've got. Aufbau, okay, which says that, the Aufbau is electrons occupy the lowest available energy level first. So before they go into the second level, they go into the first. Essentially, it's also, you can look at it like this. Okay? This is ground floor, and we've got space for 2 there. Second floor, third floor, fourth floor, we can pack more electrons in. Why? Think of it as a balloon. You've got a balloon over here, we can put 2. If you blow up the balloon, you get a bigger surface, don't you? So you can put more electrons. And if you keep blowing it, you get a balloon this size. You can now pack in loads of electrons in this one, but because this bottom one is so small, you can only put 2, okay? And each energy level that we go up, these are energy levels, right? Why? Well, because the electron over here, okay, is higher than there. This is ground floor. It can't go into a basement. So what do we say? It's higher, so it's got a higher energy level. Remember, the potential energy is height, isn't it? It can fall off this step into there if there wasn't electrons in already. So it's got a higher energy level. An electron sitting up here can bounce all the way down to the bottom. We'll have a look what happens when they do that in a few minutes. A neon light works like this. Well, so we say, right, in the first orbital, we can put 2 electrons, right? So we can put 2 there. The second level is split up into 2 separate ones, right? This first orbital here is called the S orbital, all right? So this is 1s. This one here is 2s. This one, okay, is now on the second floor, right, but slightly away from the first ones, all right? Still on the second floor, but it can't occupy that space, so it has to occupy what we call the p orbital over here. And the p orbital, because it's slightly bigger, it can take 2, 4, it can take 6 electrons here and 2 electrons there. That's why that's called an S. S, it can both take 2 electrons, right? And what it says is the lowest energy is filled up first, which means we're going to fill the 2s, right? And when it's full, we just give it its number. We say 1s has got its 2, 2s has got its 2. Now we're going to move to 2p because we need a total of 7. We need 3 more electrons to come in, don't we? To get a total of 7. We've got 2 electrons right down in the low level. We've got another 2 in the second stair. We've got another space for another 6 actually that we can pack in here. Because remember, okay, Hund's rule, every orbital is singly occupied before any is double. So Hund's rule says that we're going to start and we're going to pack. Hund's rule says that we have to occupy each level before it's occupied doubly. Okay? So you can see here we've got the Aufbau. Pauli's exclusion principle, each orbit has a maximum of 2 paired. Like that, right? So we can only have 2 in each. So that's what it would look like if it was full, wouldn't it? But now let me just remove these guys because I don't want them at this stage. Each rule, I put them in like that. Now what have we got? We've got 2p and how many? 3. That's not cubed. It's 3 electrons. So the total is we've got 7 electrons and we've put them in the correct order. Why this? Why did I put 1 arrow up and 1 arrow down? Essentially, it's called spin, okay? What we're doing is we're aligning the spin, okay? We'll come back to that when we talk about magnets and things like that, the unpaired electrons and their spin, okay? But let's just think about it just mentally as the one's going this way and the other's going that way, so they balance each other out, okay? If they were both going the same way, it would do a speed wobble. Let's just think of it like that. So they balance each other out and keep everything nice and hunky-dory. Okay, now, under this circumstance, each one is full. We've fulfilled all the rules. Right, now we look at nitrogen and we say, okay, nitrogen, possibly, there is, let's have a look. There's an open space here, an open space there, and an open space there. Right? Which means what? It means that nitrogen can take 3 more electrons. It's got 3 parking spaces, right? So it's happy to take 3 electrons and put them into those parking spaces. Why? Why? Why on earth does it want to do this, right? Because essentially, every one of these elements is trying to get to the lowest energy state possible, right? So what is it doing? It's taking the electrons to try and fill up the voids, okay? Remember what we said, if you put a liquid or a gas into it, it fills the chamber. These elements are exactly the same. What they're trying to do is they're trying to fill up their open spaces. So that, hang on, here's a space. Now let's go back. We say, hold on. Here was our sodium and here was our chlorine. Chlorine, okay, we'll go and we'll look at these in a moment. What happens here is that the sodium and the chlorine get together because they give each other electrons or take electrons away in a process, okay? Never mind, that's part of the oxidation reduction process, electron transfer. But what is happening is that the electrons are being given one over to the other, okay? So there is space for 3. Let's have a look at oxygen, okay? Let's just look at oxygen, all right? Oxygen, okay, was number 1, 2, 3, 4, 5, 6, 7. Oxygen was number 8. And when you do this, count them, okay? If you don't see the numbers, just count them. It's fine. So we've got oxygen is number 8, which means 8 electrons, obviously 8 protons, because it's balanced out. Now, what do we do now? We say, right, we've got to find space for 8 electrons. How do we do this? Well, first of all, we fill up 1s. Next, we fill up 2s, right? Next, we fill up our p. So, we've got 4. Now we're going to put 4 electrons in here. Remember, There we go. There's the first 3 filled. 1, 2, and 3. We've got one more electron to go. So this is 2p4, 4, 5, 6, 8 electrons in total. All in their relevant parking bays, nicely parked. Now we go back and we say, right, what's now? This has got 2 parking spots available. Let's just carry on. Let's look at number 9. Okay, number 9 is going to be fluorine. It's number 9, so it's got 9 electrons, 9 protons. What happens? Once again, 1s2, we fill it like that, right? Sorry, I should have drawn the blocks in over there. We say 2s2, like that. Now we go 2p, and we're going to need 2, 4, to get to 9, we need 5 electrons. Okay, how does it look? We've got this like this. There we go. Unpaired first. There we do that. Can you see we've got 1 parking spot available? So here we've got 1. Here we've got 2. And just to go back, okay, here with nitrogen, we had 3. Okay, let's just summarize that quickly. Okay, all right, let's just summarize this. All right, black. We had here, I'm just going to do it like this: fluorine, oxygen, nitrogen. Here, remember, I'm just going to put these in red. We had 1 spot, 2, and 3. Remember I said fluorine -1, oxygen -2, nitrogen -3? Here they are. Okay? It means that fluorine needs 1 electron to be full. Let's just go and have a look. If we put 1 in, we get, just change the color, okay? If we add 1 electron, we are full up. Parking space full, no entry sign, which means I'm not going to react now. I am just like a noble gas or an inert gas. An inert gas, and we'll have a look at him in a secchi, okay? Let's have a look here. Can you see? I need 2 to be full. And similarly, over here, I need 3 to be full. All right? As I said, let's look at the noble gas structure, shall we? Okay. Just gone a bit far. Let's just complete the fluorine. The next one across is neon. All right? Neon was number 1, 2, 3, 4, 6, 7, 8, 9, number 10. Okay? So neon has 10 electrons, doesn't it? I'm just going to do it above. No, I'll do it over there. It's fine. It has 10. So what do we do? 1s2, 2s2, remember, full, 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 and 2p, second floor, is full up, and we do it this way. Okay? Can you see there we've got 10 electrons, right? Neon thus has no open. In other words, on the inert gases, there's nowhere for an electron to come in. It's full up. There's a no entry sign, parking full, which means they don't react because there's no electrons to react, or no parking spaces where an electron can come in. That's why we call them inert. They don't react because there's no place for an electron to come and sit. So we can't take electrons or share electrons. There's nothing we can do. Okay? Now, you can see that -1. Now, let's just go over slightly the other way. Let us look at lithium, for example. All right? Let's look at lithium. Lithium was number 1, 2, 3. So therefore, we need 3 electrons. So what do? We go 1s2. Let's fill this up first, like that. The next one, we go to 2s, but we can only put 1. Because we've only got 3, which means, now, there's two ways of looking at this. Remember we were looking at open spots? This one's got an open spot. But what happens here, right? Lithium is a metal, right? These others that we were talking about here, okay, are non-metals. What happens with non-metals? Non-metals take electrons to fill orbitals. Non-metals take, well then what do metals do? They do the exact opposite. Metals give up electrons to drop one level down. So let's have a look. If this, in this case, I'm giving away an electron. So this electron I give away. Don't I? I'm giving it away. Then what do? Then I'm full. So metals give away electrons, which means hydrogen, lithium, how many can we give away? +1. I've got 1 to give away. I'm a plus. Minus takes away, a negative sign. Plus gives, adds to. Okay? It gives. So metals give, non-metals take. So that's why they are minus and the others are plus. So under this circumstance here, our -1 we're giving away. Well, let's have a look now. Beryllium, okay, we said that was number 2. Well, let's have a look at the electron configuration of beryllium, shall we? Okay, quickly. Beryllium is number 1, 2, 3. It's number 4, right? Which means it's 1s2, 2s2. Okay, let's just draw it like this. I'm not going to do this every time because obviously it's time. This one, okay, let's use green again, can give away 2 to give away. Correct? Which means it's got +2. Now you can see where it comes. Boron aluminium is a +3. And if you look at this, let's have a look at, lastly, let's look at boron. Is 1, 2, 3, 4 is 5. So boron is a 5. 1s2, 2s2. Remember, there we go, full. And you are full in the second level. And over here now, I've only got 1. 1p1. So this one is a metal. So immediately I know green, I can give away 3. So it's a +3. That's where the numbers come from. This is called valency. We're going to talk about valency and valency electrons, okay? And in a few minutes when we do the actual orbitals coming together. But just for the moment, that's what we're talking about here. So just to recap, first of all, we must go into level 1, then level 2, level 3, level 4, level 5s. We're only going to really deal with level 1 and 2, maybe a bit into 3. But each time we go, 1s, 2 electrons can fit in there. We go a little bit bigger, we can put more in. We can put 2 in the s here and 6 in the p. Next step, we go to the d, okay, spd. The d orbital can take more. We'll get to those in a while. What I'm going to do when we come back, okay, is we're going to look at a few more of these, okay, like sodium and chlorine and things like that. Then we're going to look at orbital shapes. We're going to look at some of the ground state, the excited state. We're going to just do a little bit more work on this electron configuration because it's such a critical part of chemistry. That's the next phase. That's the next step that we're going to be going for. Okay? Hopefully, that sort of clears up a little element there. Really, it's purely logical, isn't it? You're going, filling this. Think of it like a parking garage for electrons. You can fit 2 in first level. You can fit, 6 and 2, 8 up here. We're going to put more in the DE as we open it up, because remember, each time we go up, we're adding an electron and a proton. Okay? So each time when we add them, right, what happens is we need space to put them. And these energy levels are like a set of stairs. Okay? We'll be back, and then I'm going to continue with it, do a few more examples of this so that we've just got it under our belt, and then we're going to move on to the periodic table. Okay? There's just a lot of theory that's got to be learned, atomic radii, ionic radii, etc., etc. But thanks for listening to that. I'm hoping that these electrons are starting to make a bit of sense. It's a very schizophrenic animal. When we deal with it in physics, it gets rubbed off, it gets booted around, it gets accelerated. It goes through absolute chaos. Thanks for listening. Hopefully we'll see you on the next session where we're going to do some more of this.